So there's essentially different ways of parallelizing. There's lots of different ways to parallelize programs. But what I want to talk about now is the difference between, first of all, a serial job. A serial job is basically just a job consisting of a single task using one core, one job slot, however you want to do it. So if you run just without any parallelization, run R or Python or Bash even, it uses only one core, then it's a serial job. It's not parallelized, it's just very simple. Then there are the so-called SMP jobs, which stands for Shared Memory Parallelization. This is often realized with OpenMP, which is a way of parallelizing software. And in this way, using this form of parallelization, all the processes that are doing this need access to the memory of the node. So essentially, it needs to be on one single computer. It uses all of the different threads or processes use the same memory. So you cannot, if you have an SMP parallelized job, which I'm pretty sure that most of you will use. So if you use standard R or standard Python, something like that, it will at maximum be SMP parallelized. They all need to run on the same node. Slurm cannot do the parallelization in this case for you. And then there's also there are also MPI jobs. MPI stands for Message Passing Interface, and this works a bit differently. In this case, it's distributed memory parallelization, and you essentially, instead of having a program that uses 20 cores by using 20 threads or something, you start the program 20 times, and then the different processes start to communicate with each other directly. And this can happen across nodes, so they don't need to be on shared memory, but it can be on different nodes, which gives you the opportunity to massively parallelize it over multiple nodes. So instead of, I think our biggest nodes have 96 cores, you can have it across 10 nodes of 96 cores each, which allows you to parallelize along 960 cores, which is pretty good. But that's not that is something that needs to be built into your code. It's not something Slurm can do for you. If you have such a program, you need to start it with either MPI run or srun, which is basically the Slurm internal version of MPI run. As I already started to explain, MPI jobs are just a bunch of independent processes, tasks that are started all at once. Usually one core per task. Single node jobs usually just have one task with many cores. So if you have a single node job using shared memory, you just start one task and give it access to many cores. So and this time, in this case, task is just the program. The program is started once. You have one program that starts, and that's it. For MPI jobs, you have 20. You start your programs 20 times, each on a different node, or 5 times on one node, 5 times on the next, and so on and so on. So if you just start your program once, I'm pretty sure that's single node. That's just a single node job. You can, however, combine those two things using hybrid jobs. So you have multiple tasks, and each of these use multiple nodes. Which brings me to, how do you actually do this? So how do you tell Slurm how to use multiple nodes, or start a program multiple times, or use multiple CPUs per program? And this is done with the following options. So you have to start off, where's my mouse pointer? Here it is. You have -n, and then the minimum and maximum node count. Usually you just give one number, that's fine. You can just specify the exact number. So like, for example, if you say -N5, your program will be spread along 5 tasks, 5 nodes. Just to remember, most likely you will not use this. You will need to keep this at 1, and it is a good idea to then explicitly specify that you only want one node, so it doesn't accidentally go across multiple nodes. Then there's this, the lowercase n. This is the number of tasks. So if you have an MPI, you only need this if you have an MPI program. Then you can say, okay, start my program 10 times, and this means this you can do with this, with dash lowercase n or dash n tasks. Then there's also tasks per node. You can combine that with the number of nodes to achieve that. And for the single node jobs, most commonly used is -c for CPUs per task. So on a single core job, if you have a Python program that parallelizes along 4 cores, you would have capital N1, lowercase n1. You can leave that out completely and just say -c4, and then your one task gets 4 CPUs. Essentially, yeah, -c for single node jobs, -n for MPI jobs. And as a second rule of thumb, if you're not sure if your program uses MPI, it doesn't, because programming something in MPI is far more work than doing it on shared memory. So most of the programs will not use it. Ooh, who wrote this? Now I have a task for you. But before that, I'm going to show you a bit how this whole thing, show you a bit around that as well. So I have written a small script called Slurm resources. If I run that, it tells me I only work inside a Slurm job. If I run that inside a Slurm job, Slurm resources, it tells me a bit about how many resources are available. Oh, I'm seeing the question, what is the definition of a task? That is a good question, and it's kind of hard to define. So a task for Slurm is basically how many times your program is started. So in this case, Slurm, the program Slurm resources is started one time because I didn't give out anything else, which is why it says I am task 0 of 1. So we have one task in total. We begin counting by 0. That's how Bash does it and Slurm does it. And this job ID, and it tells you on which node it is and to which CPU. CPUs are numbered on a host, so this is how much which CPU you get access to. This is the memory. We'll come to that later. If I say srun dash, we'll start with 2 tasks. We try this, and what you can see is this program, the Slurm resources program, is not. It doesn't just have access to two CPUs, as you can see down here. I can use CPU 42 and 63. But instead, it even ran 2 times. This is the first one, and this is the second one. So this is task 1, which is the second task, and task 0, which is the first task. So this script has been called twice because it's 2 tasks. It's essentially how often your program is run that you give here. Usually you don't want this. If I have Python and try something like, I'm not quite sure what happens now. What happens if I now say print test? Okay, it only goes out once. That's, I think, due to the interactive nature of this. But usually this would have meant that this program runs twice, but you only want your Python program usually to run on a single node. Not a single time. You don't want to have like the same program running twice. You want to have twice the amount of cores for something for a program, which is why you usually use -c and then say 2 Slurm sources. So in this case, you can see task 0 of 1, so only one task. This program only, as opposed to up here, this program only ran once. You can also see it because it's only have one output and not like two blocks of output. But you still get access to the CPU number 3 and number 6. So still access to 2 different CPUs. And what I can also do is, okay, I want to have, just because why not, I want to have 2 tasks and on 2 different nodes. What happens now? You can ignore these messages for now. Later on, so for this course you can ignore that. What happens now is you have one task, this one, until here. This one ran on AMP 057 and this one ran on AMP 0595. So these 2 tasks, I had 2 tasks, ran on 2 different hosts. So if they had to communicate in some way, this would not work, except if you use MPI. Okay, regarding the question, if I'm using a regular PC with 1 CPU, 4 cores, 20 threads, so you would have 1 node, 4 cores. What? Other is already answering. So you would basically not request 8 tasks. That kind of depends. Why does it scroll down now? What happens? Sorry, I'm in the wrong window now. Okay, before I go too deeply into that, I'm gonna show for the rest of you who doesn't care what you are supposed to do. So yeah, please try these job configurations. So try to run 10 tasks. 10 tasks distributed over 3 nodes, 3 nodes with 3 tasks each, 1 task with 5 cores, 2 tasks per node, on 2 nodes with 4 cores per task. Please you can use the Slurm resources script to see if it's working the way you want to. And I will quickly go back to the questions in the chat, but now on my bigger screen. Okay, I hope you've been able to solve the exercises. If not, then I will now do it for you, because otherwise that wouldn't be fun. So 10 tasks, I essentially already did that, just a bit differently. 10 tasks, just this. So just N-N10, you will start the program Slurm resources 10 times, and they all get access to all the CPUs of that jobs. But yeah, the next one was distributed over 3 nodes. Okay, I can just add -3, so this way it will be on 1 node, 2, and 3 different nodes. So most of them are in AMP 052, but there are some that are on another one. Those obviously then don't have access to the nodes, to the CPUs of the AMP 052. Now a bit more nicely distributed, 3 nodes with 3 tasks each. So I have still 3 nodes, and I want to have tasks per node 3. Maybe it's n tasks per node, or less. Oh yeah, maybe a bit less. Yeah, that's better. So I have 3 on 058, 056, and yeah, that seems to have been correctly distributed. Now, 1 task with 5 cores. Now we come to the single node jobs. So we want to have 1 task -1 and 5 cores. I'll do this. So I only start the Slurm resources script once, as you can see, and it's only 1 output. I'm on this host, and I got 0 CPUs 0 to 4. I mean, it's always starting at 0. And last but not least, 2 tasks per node on 2 nodes with 4 cores each. So I want to have 2 tasks per node on 2 nodes with 4 cores each. So, okay, these are, yeah, I have 2 tasks on 056 and 2 tasks on 052. So that's my 2 nodes on two tasks. Is that correct? Yeah. It's two tasks per node on 2 nodes, and each has like 1 to 8. The CPUs 1 to 8. So each task got 4 CPUs. And I mean, yeah. Okay. That's it for that. The important thing to keep in mind is that well, not the important thing, but one important thing, if you don't have MPI, and as I said, if you are unsure about it, you won't. You should mainly use essentially always use just one task, one node, one task, and then just play with the C as a parameter, and I don't know, take 50 cores. Okay, let's go on. Now we talked about CPUs and how to get more access to more cores and more nodes and stuff like that. Now the next thing we have to talk about memory. You already might have seen that that the script already told you something about memory, and if you were very alert, you might have noticed that the memory you got changed sometimes. But so far you might have even seen a pattern. I'll explain it soon. But the main option, the main way to get more or less memory is to use. There are 2 different parameters for that. Either --mem, and then you can give the size in a unit of choice. I think default is megabytes. Or so this would be memory per node. And if you want to have that per CPU, oh, that's wrong. That's not per task. That's per core. Then you need to use mem per CPU, as the thing itself says. So if you don't give any options, then each partition has a def mem per CPU option, and you can take a look at this with this command, or take a look at this. We have this on the website as well. There's for each, I mean, it's kind of hard to read, but for each partition and kind of node type, we have the different amount of memories they have here. So, but essentially, if you want to know how much, for example, the medium partition has, you just say as control. Let's take this, and I'll do this and this. Medium, and what you can see is def mem per CPU, and it says 3770. So it means that you have 3.77 gigabytes of memory, so 3,770 megabytes of memory per CPU available on your node. So if you have 10 CPUs, you get 10 times that, which I'm going to show you now. So this was something you could see before. Yeah, let's use 10 times. What can you see? You get, like, you've checked this. You see, you have per CPU, you have 3,770, and if you can see down here now, there's 37,700 megabytes of memory available on this host for you. If I want to change that, I just want to have 5 gigabytes. I don't know why I would do that, but sure, why not? I can do this, and suddenly, oh yeah, there's only 512 megabytes, 5120, because it's like the usual conversion between megabytes and megabits and everything. Anyway, around 5 gigabytes of memory available. Now, if I say mem per CPU, I would have, does that make sense? Yeah, 51.2, so 10 times 5 gigabytes. So 5 gigabytes was that many MB, and now 10 times that is obviously this. Okay, going back. Yeah. Right, so now again, you can do something, because it's more fun if you do stuff. Please play around with the different options you have here. Just try a bit with different combinations of number of cores, tasks, nodes, and everything. Take a look, like, for example, 1 core and memory 4 gigabyte, see 3 tasks and 2 nodes, and the different effects of mem and mem per CPU, and or just 20 tasks and see the distribution of memory over different hosts, depending on what you use for these. Just play around with it. Use the Slurm resources script to see how much you have on the host, and yeah, that's your exercise for now. So have fun. I'm gonna see if you have questions. Since I've been asked now more than once, so Slurm resources should be available to all of you just on the command line like that. It is also, if you, I'm not sure if others mentioned it, but if you, there's a command where is, which displays where the command is. And if you type that, you will see it's at opt slurm bin slurm resources. You can even take a look at it, and there's nothing that much special in it, happening in here. I'm just checking if I'm inside a Slurm job, because if I'm inside a Slurm job, this variable is set, and get some information out of the out of some specific subsystems of Linux about the CPUs I have and the memory I have. It's just a very simple Slurm script, bash script. Okay, most of you are done. I'm also finished. Ha. No, I'm gonna vote for maybe, just to confuse people. Then I will show you how this works, just for the few people that might be there who didn't do it. So the first thing was 1 core and 4 gigs of memory. 1 core and 4 gigs of memory. It's easy. I could also do, as this is a single host, I could also do this. 3 tasks and 2 nodes. 3 tasks and 2 nodes. And I'll just keep it at, so this time for the 4 gigabytes. And what I can see is, there are 2 tasks on AMP052 and 1 task on AMP056, but nevertheless both only have 4 gigabytes. So this node didn't get more memory, although it has twice the amount of tasks that this one has to do. So this is kind of bad, but you can also do per core to make it more equal. No, per CPU. As you can see, how it doesn't matter how long you work with Slurm, you still get the options wrong. And you can see now in this case, this node got 2 tasks, but also twice the amount of memory, which is more fair, obviously. And 20 tasks, and see the distribution of memory over hosts. Okay, why did I do that? Oh, let's leave out this and just say 20 tasks. No, it's all on one host, I think. Well, that's kind of unspectacular. Let's add N3. Oh, why do I have... Oh, this was what I wanted. Now. So you can see that this one only has one task, and this one has quite a number of tasks. Right. 52, 52, 52, didn't I say? Ah, I have one on AMP 058, which has 4 GB, one on 056, which is 4 GB, and the rest landed on 052, which has the rest of like 18 times 4 GB. That's just what I wanted to show. So it kind of depends. If I did this, however, then again you would have 4 GB on every host, no matter how many tasks were on that host. Okay.